Okay, so what do we have to do? We solved the Eichel equation last time. The Eichel equation showed that we end up with straight lines in free space. So each of the rays are straight lines. And the parameterization of them is straight line parameterization, right? Some vector B points to a point on the line, and you have a tangent vector to the ray, and you can multiply that tangent vector by some parameter, say sigma. Today we're going to solve the transport equation. So the transport equation governs the electric field amplitudes along the ray. By solving this, we'll be able to come up with a formula how to propagate the amplitude vectors E along a ray. So since rays are orthogonal to wavefronts, the tube of rays intersect a wavefront surface, sigma 1 and at sigma 2. So at some point on this ray, here's an axial ray. At some point on this ray, we have some point sigma 1 and some point sigma 2 on that ray. And at that point, the bundle of rays, the flux tube of rays, carves out a cross-sectional area dA1 and dA2 at some other point, right, at sigma 2. In lossless media, we know that the power which flows through the surface area dA1 must be conserved, and thus should also flow through area dA2. To state that mathematically, we say that the divergence of the pointing vector is equal to 0, right? That means any power entering a point must leave that point. There's no dissipation, right? There's no sources or sinks of power density flux, right? All right, so evoking the divergence theorem, we can integrate the above result. So we integrate over throughout the volume V of this flux tube of rays, for example, that goes here to here. So we integrate over this volume V, which has surface S. So the integration throughout the volume of the divergence of S t hat dV, we can write using the divergence theorem as the closed surface flux integral through the surface. So this really should have a circle like that, right? Okay. ST dotted with ds, where ds is the outward normal. That has to equal to 0. All right. We showed power flows in the direction of the rays, and hence no power flows through orthogonal, to the flux tube, right? Hence the above results. So that means the contribution from the sides of this sort of a conical shaped cylinder, the contribution out to the flux out of the sides is 0. So you just have the flux exiting the end caps and entering the first end cap, right? If you take the difference between that, then you get this expression here, right? Which says that the power entering this face must exit this face because there is no dissipation and the power doesn't flow orthogonal to the rays. All right? Okay, good. All right. So now let's solve the transport equation. Let's start from the transport equation. We got this from the wave equation and the Lunenburg-Klein asymptotic expansion for the electric field. First thing we note is this term gradient of S dotted with the gradient. The gradient of S dotted with the gradient is an operator. It operates on some function, right? And we can write that as T dotted with the gradient because by the Eichel equation, right? So we have the magnitude of gradient of S squared is equal to 1. And we can write that as the gradient of S dotted with the gradient of S, right? And if that has to equal to 1, then that means that this has to be a unit vector. We can call it t hat for the tangent direction to the ray. So gradient of S we can say is equal to t hat, right? In free space. Okay, so gradient of S dotted with gradient is equal to t dotted with del, or whatever you call that operator. Sometimes it's called nabla. We can write that as partial by partial sigma, which is a derivative in the direction of the ray, right? That's what t dotted with the gradient means. Remember, this gradient here is partial by partial x, partial by partial y, in rectangular coordinates, if we were working in rectangular coordinates. And if you take the dot product with t, it's like a directional derivative in the direction of t. All right. And we know that a directional derivative in the direction of the tangent to the ray is also partial by partial sigma. So we can write this as partial by partial sigma. All right, let's consider only the 0th order term, so m equal to 0 here. And therefore, e to the minus 1 is equal to 0. That means the whole right-hand side is equal to 0 because we're only considering m equal to 0. And we end up with this expression here. This is the expression in your book. All right. To calculate the magnitude of E naught, we can take the dot product of both sides with E naught conjugate because we want to form magnitude of E naught squared, right? So the way we can do that is take the dot product of both sides of this expression with E naught conjugate, and we end up with this expression here. Now, we see a term here that's partial E naught partial sigma dotted with E naught conjugate. And we can recognize that as one of the terms of the product rule of partial by partial sigma E naught dotted with E naught conjugate, right? Because here we have, here's F and here's G. Here we would have F dotted with partial G or G prime. Let me say it that way. Here's F, here's G. So here's F dotted with G prime plus G dotted with F prime, right? All right. So that means that this term is this term, and therefore we can write that as this term minus this one. And that's what we've done here, this minus that. That is this term, right? All right, and then the rest of it's the same. Very good. To eliminate the second term, so I guess it's the second term here, to eliminate this term, now we need to get rid of this term. How can we do that? Well, we're going to form the conjugate equation and add the two together. So instead of taking the dot product of this equation with E naught conjugate, we're going to conjugate this equation and take the dot product with E naught to form the conjugate equation. So that's what we have here. Conjugate of the first dotted with E naught. All right. And if you do the same thing, then, or we could distribute this dot product here. So we get partial E naught conjugate dotted with E naught with respect to sigma plus 1/2 del squared S E naught conjugate dotted with E naught equal to 0. All right, we do the same thing with the product rule, and we can replace this term here with these two terms. All right? Okay, very good. All right, so now we have to add the two together. So here's the first equation, here's the second one. We're going to add them together. And what we will obtain is the following. We get twice this term because these are the same, right? So we get two of those. And then we get minus E naught. So this term comes from here. And this term comes from here. So we added those two together. And then there are two of these, but these are both 1/2. So you just get rid of the 1/2 and you get this expression, right? All right, good. All right. So what do we do now? Multiply through by a negative. So we change the signs of everything, right? And now we'll notice that we have E naught dotted with partial E naught with respect to sigma plus E naught conjugate dotted with partial E naught with respect to sigma. And that we can recognize as partial by partial sigma of E naught dotted with E naught conjugate. All right, so we replace that with this, right? Everything else is the same. Now we have minus 2 of these and 1 of these. That becomes minus 1 of them, right? So minus 1 of those. And this term stays the same. Okay, now we just multiply back through by a negative, and we're here at this stage. All right? Okay, good. All right. Next, we divide through by E naught conjugate dotted with E naught. Why do we want to do that? Because we want to get rid of, where are we here? We want to get rid of this, right? Because remember, del squared S, this is like that's a scalar quantity, right? Okay, that multiplies into all of this. So if we divide through by 1 over E naught conjugate dotted with E naught, multiply both the first and the second term by that, then this will cancel with this. All right, that's good. So we end up with this only. And now we have this expression to deal with. So how can we deal with that? Well, note that the derivative with respect to x of ln of f of x, if we use the chain rule, we get 1 over f of x df of x dx, right? All right. So what do we have here? We have the natural log of this expression, right? So that's like this, and we're differentiating with respect to sigma. So what would we get? We would get 1 over the argument here, x, which is this. So 1 over that is here. And then we get df dx. So here's d by d sigma, and then here's the f. Yeah, so that's how you go from that line to that line. All right. Now, we have this expression which is valid at a point, but we want to find how it varies from point A to point B, right? We want to integrate this expression along some path from point A to point B on array. All right, so we're going to integrate from point A to point B, just 2 points on the ray, and integrate both sides with respect to d sigma. So we're integrating along the ray. And by the fundamental theorem of calculus, we end up writing the left side as ln of epsilon, or sorry, E naught dotted with E naught conjugate from B to A, or from A to B rather, is equal to the right-hand side, integrated from A to B del squared S d sigma. All right. If you evaluate the result at the endpoints of the integration, then you get ln of B divided by ln of A, right? Because here we would have ln of B minus ln of A. So this would give you ln of B, ln at B minus ln at A. But if you subtract 2 natural logs, you can write them as ln of B over A. All right, and then that's equal to the right-hand side still. Now to get rid of this natural log, what we're going to do is take take both sides to the power of E. And we end up with E at B. So E naught dot with E naught conjugate, which is related to the amplitude of E, right? E naught dot with E naught conjugate at B is equal to E naught dot with E naught conjugate at A, multiplied by E to the power of minus integral from A to B of the Laplacian of S d sigma. All right? So we're getting somewhere, but there's still this integral of the Laplacian to deal with, right? All right. So note, since del squared S is equal to the divergence of the gradient of S, which is equal to, which is equal to the divergence of t hat, right, by the Eichel equation, then what we can say is the gradient of S is a unit vector in the ray tangent direction. We kind of already said that, right? All right. So del squared S we can write as divergence of t. So that's all we've done here. We've rewritten the integrand as the divergence of t hat. All right? Okay, next we use a theorem of differential geometry, and that is in this presentation. I'll show you in the next slide or two, so it will be proven that the divergence of t is nothing but twice the mean curvature of the wavefront. All right? Okay, so the divergence of t is twice the mean curvature, which is kappa 1 of sigma plus kappa 2, right? Which is 1 over r1 plus sigma plus 1 over r2 plus sigma. Yeah? All right. So let's plug that back into our integral, into our integrand, and we get this expression here, right? Now we're going to integrate that, and what do we get? We're integrating 1 over r1 plus sigma, basically, right, from A to B. So what do we get? We get ln of r1 plus sigma plus ln of r2 plus sigma from A to B. All right. Now we have a natural log and a minus 1/2, so let's bring that upstairs. So, or to the power, so we get square roots of all of that, right? Okay. Now what we're going to do is plug in these limits, and we're going to treat the limit A like the beginning of the integration interval, so it's going to be basically 0. So we get r1 of A, here we get r1 ln of r1 of A plus B, so we're plugging in B first, and minus, so the other one is here, ln of r2 plus B, right? So we plugged in B for those two terms, and then we do minus the result with A plugged in, right? So minus ln of r1 of A, because at that endpoint sigma is equal to 0, and ln of r2 of A. All right. Okay, so now what do? Let's see, we combine these natural logs because there's some minuses here, right? Here and here, so we can combine those, and some plus signs too. So the plus signs become multiplication. ln of A times B is equal to ln of A plus ln of B. And the minus signs become division. ln of A minus ln of B is ln of A over B. All right. So we get this expression here, right? One natural log now because you combine them all based on the properties of log. And at the next point, we have e to the ln. So that those are inverse functions. So what do we get here? We get just this integrand, right? Or this part of the exponential. Great. All right, let's take this square root into both of these terms and rewrite it as a product. What do we get? We get something familiar, yeah? This is starting to look like our divergence factor. All right, great. So we end up here, right? So we have this expression. And we can rewrite this as dividing through by R1 and R2 for the second term. And what do we get? We get 1 over 1 plus B over R1 of A multiplied by the square root of 1 over 1 plus B over R2 of A. All right. Well, the square root of the numerator is just 1, so we can keep the square roots in the denominator only. And that is our divergence factor. So what does this show? This shows that the electric field amplitude, E naught of the zeroth order term, at some point sigma on a ray, is related to the electric field at some reference point sigma naught on the ray, multiplied by this divergence factor. And that came out of Maxwell's equations and the Lunenburg-Klein expansion, right? So this is not based on geometry. Of course, you can arrive at the similar result using geometrical arguments. But here, we've directly derived this from Maxwell's equations, which says that the amplitude is transported along a ray according to this divergence factor. Very good. So combine this with the continuation of the optical path length along a ray, and we can define a formula for the continuation of the electric field along a ray. All right? So all of this stuff that we've been learning, we learned a bunch of differential geometry, and then we learned how to solve or how to satisfy Maxwell's equations using the Lunenburg-Klein expansion, and out came a couple of different equations, the Eikenall equation and the transport equation. And restricting our attention to the zeroth order term, m equal to 0, we derived expressions for the continuation of the phase and the continuation of the amplitude. So at the end, after all those derivations, solving those differential equations, how did that happen? All we needed, or all we need in the end is this formula, okay? So remember, the continuation of the phase function, S at R equals to S at R naught plus sigma minus sigma naught. And along the axial ray, if we're going to use pencil coordinates, that's equal to S at 0, 0, Z is equal to S at 0, 0 plus Z. All right, so that makes sense, right? The phase is related to the length, optical path length of the ray. So if I have a optical path length of Z of the ray, then I can multiply that by K to get the phase, right? It's related to the K vector, how far we've gone throughout space, right? So here's a little image here. Okay, so first here. So the electric field for the zeroth order term is equal to, at some point R, is equal to the electric field at some point R naught, and the change in the amplitude multiplied by the change in the amplitude using the divergence factor, and the change in the phase using the optical path length from sigma naught to sigma, right? So that's all that matters at the end. And it's exactly what you'd expect, right? There's nothing new here. We're talking about an electric field which is traveling along some direction, in this case a straight ray, in the direction of a straight ray, in the axial ray, and we're saying that it incurs phase delay according to e to the ik, z naught minus z or whatever, or z minus z naught. The only thing kind of new is this divergence factor. How does the amplitude change? But now that's because we're not talking about plane waves, right? This looks locally like a plane wave, but its amplitude is changing because really it's part of a, not a spherical wave, but some generally curved wavefront. And the amplitude of the electric field is related to the change in curvature of that wavefront, right? And it kind of makes sense intuitively. Think about this. If I have a point source here of 1 watt and it radiates in lossless media, then let's say it radiates a spherical wave, but for now let's consider it in the plane of the board as a cylindrical wave, right? So just it radiates a circle here, right? And if I were to integrate the power density here along this path at radius r, say r naught, then how much power should I get if I integrate the power density? That's right. Let me draw this a little nicer. 1 watt, radius r naught. This defines some kind of circle. The power density at r naught, well, let me not make that a vector since it's a cylindrical wave. The power density at r naught, right? If I integrate that power density at r naught, then I better pick up 1 watt if it's a lossless medium, right? Because where did the power go? If I integrate power density, then I should get power, right? And I'm talking about the flux of power that's exiting through this surface at r naught, right? So you should get 1 watt. All right, great. All right. Now, what about this circle here, which is at radius r1, for example? And I integrate the power at r1. What should I get? 1 watt again, right? Okay. However, what is the strength of the electric field at this point, for example?
1 over R0.
That's right. So remember, the electric field at this point decays as, so in order to have 1 watt here, right? Say this is spherical coordinates, right? So these are spheres, but this is a cross section of it. Say that at this, if I were to conserve power, so they get 1 watt to the sphere with radius r naught, then what does my, and I get the same 1 watt at r1 throughout that sphere. Then what does the field components have to decay with in order to maintain that conservation of power? So I have E, I have H, right? E has to decay proportional to what? Square root of r if it's a cylindrical wave, that's correct. But if it's a spherical wave, then it's 1 over r. It has to be, right? Why? Because and H has to decay proportional to 1 over r as well. Why? Because the power, this is proportional to E cross, or E times H, right? So let's just say times H. It's really the cross product, right? But let's say that it's proportional to the product of E and H, which is 1 over r squared, right? And we're saying the surface area of this sphere grows as r squared. So that means that the power has to decay as a function of r squared in order for you always to get 1 watt. It has to be independent of the sphere's surface area, right? So that means the r squared in the 4 pi r squared surface area, if I say P times S, the surface area, has to always equal to 1 watt, then, and that means P times 4 pi r squared has to be a constant with respect to r, then P has to be proportional to 1 over r squared. Yeah? All right. So, good. So what does that mean? That means that, and these 1 over r's are kind of the radius of curvature of these things, right? Or the curvature, rather. R is the radius of curvature, and 1 over r is the curvature. So there's a relationship between the decay of the field components and the curvature of these surfaces. All right. But here what we're saying is this might not be a sphere. It might be some arbitrarily shaped wavefront. That's kind of too cloudish, but some arbitrarily shaped wavefront, right? So now we're talking about, okay, let's consider this as, let's break the wavefront into pieces. Instead of solving what they call full wave solvers, where you solve the whole electromagnetics problem and the whole domain at the same time, we're going to discretize the wavefront, and we're going to discretize into patches. And each of those patches we're going to solve independently, which means we lose the coupling between different parts of the geometry, right? Geometrical optics is a inherently local technique, meaning that I'm solving the problem piece by piece. I take the wavefront, here's a surface, right? Sigma, for example, and I consider only this ray reflecting off of this surface, and I find the wavefront there. Then I choose a different ray, and I reflect that one, and I find the other piece of the wavefront there. At the end, I reconstruct the reflected wavefront. but there's no coupling between the field at this point and this one, because I'm considering local phenomena. Everything, all this reflection that's happening here is local, depends on the field only at that point and in the neighborhood of the point, right? So that's the limitation of geometrical optics, but we're assuming that things are high frequency, so that's probably a good approximation. It is a good approximation, right? Anyway, you break this wavefront into small pieces and you consider the curvature of this differential wavefront and that's carried by that ray.
In the method of moment, we take care of the coupling between.
Oh yeah, that's the power of moment method. It's all the couplings considered from all parts of the structure. It's an exact solution in a sense. All right, that's full wave solution as well. Okay, so we can rewrite this as the electric field at some point R is equal to the magnitude of the electric field at R naught multiplied by the divergence factor and multiplied by e to the IKS, the phase at point R naught, plus the new phase due to the path of the ray, right? So it should all make sense now. And that is equal to this expression. So now we have a way to take the electric field at some point on a ray and find what the electric field is at another point on the same ray. So we only need to know the electric field at some reference point, and we can propagate it or transport it along a ray to any other point. All right? Good, good. So that's very easy then now to trace rays. You can write programs to do all of this, and you're going to in your homework. So here's the proof. I don't think I'm gonna go through this. You guys can, because we have a lot to do. You guys can go through this slide in the next one. This is how you prove this theorem here is equal to the divergence of t. All right? Read that on your own time. Now we're going to get into putting everything together that we've learned to solve geometrical optics problems and to calculate reflections from surfaces. So for a given incident field, our task will be to determine the total field everywhere. All right? The incident field produced by the source in the absence of what we're calling the screen sigma. So here's some metallic, perfectly conducting screen, and we're going to call that sigma, is described by the asymptotic series of the form of Lunenburg-Klein, right? All right. According to geometrical optics theory, the incident field is blocked by sigma and casts a shadow behind it. Whether or not, so here's all back here is zero field, right? Whether or not an observation point R is in the lit or the shadow region can be determined by drawing a straight line from the source point R naught, to the observation point R, right? So you pick an observation point, here's R naught, this is the point source, right? And you pick an observation point, say R out here, you draw a straight line from these two. If it doesn't intersect sigma, then that point R is in the lit region. If it does intersect sigma, then it's in the shadow region, all right? So you're gonna do a lot of these things when you write these programs in geometrical optics. Intersection of surfaces and rays, right? That's an easy thing to do. You have a vector R, which has x, y, and z components, x hat, y hat, and z hat components. You have a parameterization of a surface, R, in terms of, okay, so you have a surface, some ellipsoid, for example, and the points on this surface are described by R of u and v, right? But that has some x, some y, and some z components, right? All right, you have this ray here, which you can parameterize as, let's say the starting point is 0 if it's at the origin. But if it's not, then the parameterization of that ray is R of t is equal to t into A plus B, where B is some point on the ray, a position vector is some point on the ray. Let me draw it like that so it's nice and clear, all right? So this anyway is the vector R of u and v. So you have some ray, let's say the ray is coming like this. You have some point B on the ray, then you have some tangent vector A, right? So what you want to do, and this R also has x hat, y hat, and z hat components. So what you're going to do is solve for the x, y, and z in space, of which these two share a solution, right? This parameterization of this line, this ray, has values of x, y, and z which are on the ray, right? On that line. And this surface also has a parameterization which has points of x, y, and z which are on its surface. Only this point here shares the same x, y, and z, right? So the way you solve that is you solve three equations with three unknowns. The x component of this line vector, or this array, the line has to equal to the x component of the surface. The y components have to be equal and the z components have to be equal. And you can solve for x, y, and z. The x, y, and z in space. This point has coordinates, you know, x naught, y naught, z naught, right? So you can do a lot of that when you write these programs. Anyway, so it's easy to find whether or not the array intersects a surface. You're going to need to do that. All right, so we can define a shadow indicator of the incident field. It's called epsilon incident, and it's equal to +1 if r is in the shadow region, or -1 if it's in the lit region. There should be a space here, of the incident field, okay? Also, we define a shadow boundary where the last ray, which does not intersect sigma, defines what's called the shadow boundary. So on this side of the shadow boundary, it's lit. On this side of the shadow boundary, it's dark. All right? Very good, very good. All right, now we're going to define the incident field in the presence of the screen using this cookie cutter operator, which is theta. So the argument of theta is minus epsilon incident, and theta is a step function. +1 if x is greater than 0, 0 if x is less than 0. So that's nothing but, here's x. If x is greater than 0, it's 1. If x is less than 0, it's 0. It's a step function. And you pass into it the shadow indicator. And you multiply that by E incident. So all that's going to do is, normally E incident, point source here, it radiates everywhere, right? When we solve problems analytically, like in last semester, we say the incident field is omnipresent everywhere, right? And then we introduce the scatterer into the incident field, and it generates a new field called the scattered field. And the superposition of the incident omnipresent field and the scattered field generates the total field, right? Now, what we have here is a little different situation. We have the incident field in the presence of the screen. So the incident field now is not omnipresent, but we take care of these shadows, right? The shadow regions. It kind of makes sense, right? I mean, okay. We'll leave it at that, yeah? All right. Now we're going to define the reflected field similarly. The reflected field has its own cookie cutter, and the reflected field also has its own asymptotic expansion, and it has a reflection shadow indicator, and it's defined in exactly the same way. So the reflected field is exactly the same thing, right? And there's a shadow boundary for the reflected field. So here's R naught and the source. Then we have things that reflect off of the screen, and the last ray that reflects off the screen is the shadow boundary for the reflected field. Because why? To this side of the shadow boundary, E reflected is there. This side of the reflected shadow boundary, E reflected is equal to 0. Yeah? Okay, good. Very nice. So now let's compute the reflected field. We know the incident field. Now we're going to compute the reflected field. All right, great. So consider the reflection from a typical point O on screen sigma. We'll call that the point of reflection. Here's point O, or that's a wavefront rather, sorry. The sigma refers to the scatter. There are three quantities involved here that we have to define. The incident pencil, the reflected pencil, and the screen sigma, okay? We've done some of this already. So the incident pencil, we're going to introduce the rectangular pencil coordinates, x1, I, x2, I, zi equal to x3, I, to describe the position in the incident pencil. We did this before, right? So zi coincides with the axial ray and passes through point O. So here's the axial ray. And remember what we did here. The axial ray is there. Here's a point O on the wavefront. Here's the axial ray. We aligned the z-axis of our local coordinate system for the pencil coordinates of the incident wavefront with the axial ray. Then we define two orthogonal axes, x1 hat and x2 hat. right, for the incident pencil coordinates. And we form a second order quadratic approximation in this coordinate system of this wavefront surface using the curvature matrix of that wavefront, right? Here, just like this. The second order approximation is this part. All right, and remember what this does. This says that the phase at some point, so x1 hat and x2 hat, if I move along x1 hat and x2 hat, I might get x1 incident, x2 incident here, right? Okay. At that point, what is the phase with respect to this coordinate system at this point? Well, it's the phase of the axial ray at this point, right? Wherever the reference point is for that, it could be at this origin or it could be down here, plus the propagation distance along the axial ray, plus the change in phase, right? The phase front defines the phase. So this tangent plane, say it's planar like this, but this point here on the surface is a little bit below the tangent plane, right? There's an epsilon factor here. This accounts for that. We did that last lecture, right? Okay. So from here on out, we'll always assume that x1 incident and x2 incident, the local pencil coordinates for the incident pencil, always coincide with the principal directions. Therefore, our curvature matrix for the incident pencil is 1 over R1 incident plus Z incident and 1 over R2 incident plus Z incidents, right? Diagonal. Why is it diagonal?
Z is the direction of x.
Okay. So how do we get a diagonal curvature matrix? Very nice. When we're in the eigenbasis of this matrix, right? The eigenbasis are the principal directions. So that means that x1 incident hat and x2 incident hat are aligned with the principal directions of this wavefront surface. That's the way you get this diagonal matrix, right? Okay, good. Let's consider the vector components of the amplitudes of EM incident, all right? So first off, what does this equation allow us to do? This allows us to find the phase at some point. Okay, we kind of said that. At some point, not along the axial ray, but still in the pencil, right? We're going to do the same thing for the amplitudes. Next, consider the vector components of the amplitude vectors EM. We resolve the amplitude vectors into longitudinal and transverse components with respect to each individual ray. Now we're considering paraxial rays here as well, all right? Because we need to be able to describe the electric field for at the vector at different points in this tangent plane, right? So to accomplish this, we introduce 3 local orthonormal base vectors at a point R. All right. So here's a point R, right? That says R there, so that means R is here. That's R, right, with respect to this origin in the pencil. So it's a paraxial ray. And that vector, so in this coordinate system, Z, x1, x2, this vector to this point, R, has x1 incident, x2 incident, Z incident as its coordinates, right, as its components. All right. So what do we need to do? We need to describe this coordinate system, sigma 1, sigma 2, and sigma incident. These are all little sigmas now, right? So here we have x1, x2, and z, pencil coordinates for the axial ray, right? The paraxial rays, we're going to define a new coordinate system, sigma 1 hat, sigma 2 hat, and S incident, I guess, which is sigma 1 hat, right? Or sigma hat, rather. So how do we find the components in terms of these coordinates? All right, sigma 1 incident is this vector. That's equal to x1 incident, which is this vector, minus z, minus the z, this component, multiplied by x1 over r1 incident plus z1 incident, okay? That comes from this expression here. So you need to subtract off part of the z component there, right? So it's a projection. All right, sigma 2 hat similarly, like this. And then the gradient of sigma, or the gradient of SI, so here's SI. The gradient of the local surface around that point is equal to sigma, sigma I, And we can find that by taking the gradient of this expression here. So here's our S, right? If we take the gradient of this is valid for the paraxial rays as well, right? Because this axial ray has Z. This paraxial ray we call S, right? This is valid for any R. So this R, for example, if we take the gradient of this, then what we find is a normal to the surface. A normal to this surface, right? So that's here. We just take the gradient of that and we get this expression. All right. Very good. Thus, at any point in the pencil, we represent EM, the electric field vector, in terms of these components, sigma 1, sigma 2, and gradient, or sigma, basically, right? Which is in this coordinate system. So EM at a point R in the pencil, right? Described from this reference origin. The electric field there has sigma 1 component, sigma 2 component, and a sigma component, all right? All right, things probably look complicated right now because you're learning a lot of stuff and you're solving a bunch of PDEs and we're kind of breaking things into rays, a lot of differential geometry. So things are probably, you're learning them in pieces here, but you haven't been able to put it together in your mind to solve a problem yet, right? And I get that. So what it'll become much more clear when you go to solve a problem, right? You only need a couple of these results in order to solve the problem. All right? So it'll become much more clear. All right. In an incident pencil, the phase function and the amplitude vectors now can be described as, so we already derived this, how to describe the phase in the pencil with respect to the origin located at along the axial ray. Now we can define the electric field vectors too, right? And these are nothing but the sigma 1 hat, sigma 2 hat, and the sigma hat or gradient of S, right? Because we said here, this sigma 1 hat, sigma 2 hat, gradient of S, well, those are these expressions here. If you substitute those into here, then you get these expressions, all right? So I will do an example where we do calculation of some wavefront reflecting off of a surface, all right? And I'll show you the code and we'll go through that whole example next lecture. So you'll see how it's a lot easier than it looks, all right? Okay, reflected pencil. Okay. So these formulas allow you to calculate the phase and amplitude at any point in a pencil in terms of the pencil coordinates and the base vectors. So in terms of this coordinate system, any point in this pencil on this part of the axial ray, on this part of the axial ray, or paraxial ray, paraxial ray, in this coordinate system, on this point or this point of the paraxial ray, we can define the electric field and the phase function, right? Okay, good. And what is it a function of? It's a function of the Q matrix, right? Basically boils down to the Q matrix, and there's the R's, which are also the radii of curvature, all right? Good. So the reflected pencil, all the formulas are the same, except we replace I by R, all right? Now we need to define the screen coordinates, all right? Okay. In the end, you're not going to need to think about all these coordinate systems. We're going to use them to derive a result, all right? Okay. The screen sigma now at a point of reflection O, so here's sigma now, here's O, at the point of reflection, the axial ray in the incident pencil meets sigma. The axial ray of the incident pencil, so here's the incident pencil, it meets sigma at the point O of reflection, the axial ray. But remember, there's also a bunch of paraxial rays. We need those paraxial rays because we have to do phase matching at the boundary to satisfy the boundary condition, calculate the reflected Q matrix over an area carried by the axial ray, right? We need some information about the curvature of the surface at the point of reflection in order to accurately calculate the reflected Q matrix. So we can't just consider the axial ray reflecting off like that. That is like the sort of the optics where you just calculate paths and lensing and stuff like that, right? You don't consider the amplitude. But if you want to know the amplitude, you need to know locally around this point what the curvature looks like. And the only way to do that is to follow a pencil or a flux tube of rays reflecting off of this surface. right? Because we need the differential surface area in that flux tube of rays to reflect off of it as well, right? The, where is that differential surface area thing? We just looked at it, right? We need this, right? We need these differential areas to calculate the amplitude. So we need the axial ray and the paraxial rays that form a tube. So we need to calculate the phase and amplitude at all points in the tube so that we can apply the boundary conditions. We're going to do that, okay? All right. So, good. All right. Okay, so at the point of reflection, we introduced three orthonormal base vectors, now x1, x2, and x3, but they have superscript sigma now. So here's x1 sigma, x2 sigma, and z sigma. So the surface has its own coordinate system. Z sigma coincides with the outward normal at O. And we said for surfaces and wavefronts, the normal is always chosen to be toward the source, right? So we're assuming the incident field's coming this way. That means the normal is always back toward the source, right? Okay. X1 sigma, X2 sigma coincide with the principal directions of sigma at O, right? So these are the principal directions of sigma at the point of reflection. In the neighborhood of O, sigma can then be approximated by a quadratic surface. This thing again, right? The quadratic approximation, second order approximation of the surface in terms of the curvature matrix of the surface now. And we have the diagonal curvature matrix of the surface because we're in the principal direction, in the principal coordinate system, right? Yeah? All right. At an arbitrary point R in this coordinate system now, so here's say R with respect to this origin, on sigma and in the neighborhood of O, we define three local orthonormal basis vectors. So here's the same thing, right? It's the same thing as before. Here's a point R. So here's the point R. Here's R, right? And we have another local coordinate system here, which has n as the normal, sigma 1 epsilon, and sigma 2 epsilon, but they're all... So it's the exact same thing we did with the pencil coordinates, right? It's a paraxial coordinate system. It's a way to describe the surface at different points than the axial ray, or the normal to the surface in this case, in terms of the coordinate system, in terms of these components, right? All right? Okay, at O, okay, obviously at the origin, this local coordinate system corresponds to this one, right? They're the same if R is equal to 0, basically. All right. With the description of the incident pencil, reflected pencil, and the screen sigma, okay.
So we have one coordinate system for the screen, the other one for the incident ray, and the other one for the observation point.
Yeah, so let me back up real quick. All right, so here we have three entities to consider, right? The problem we're solving is some curved surface. That curved surface has an incident flux tube of rays, right? That incident pencil, and that incident pencil and a reflected pencil, right? And in order to describe the electric field and the phase function in the incident pencil, we have to be able to describe things in terms of the coordinate system, which is centered about the axial ray, right? So we have to describe other points, other phase functions and field vectors in the incident pencil with respect to the coordinate system centered on the axial ray, right? And therefore, so to define electric fields that are orthogonal to rays, right, then we want to have a local coordinate system here that has transverse and longitudinal components. I want to describe these vectors in terms of these components, right, in terms of those vectors. All right. So this we have to be very comfortable with. Does everybody understand this? So what does this mean? The phase function at some point R in a pencil, right? So what coordinate system is this R defined in? Very good. Right? That R is in this. The axial ray has a coordinate system on it. X1 and X2 are in the principal directions, and Z is tangent to the ray. It's along the axial ray, right? So with respect to that coordinate system, we have an R, a position vector R. that position vector r is here. We can find the phase function at different points in the pencil using that coordinate system, which is the phase, so for some reference point, so at the origin, is that phase 0 or not, right? Where's the phase reference? It could be further back, right? Plus the distance traveled since that phase reference point. That brings you to the phase at the axial ray at point O, right? Plus, or no, sorry. This position vector R, right? So this part is the phase, phase of the reference, since the reference point. That brings you to the origin. Then you have Z incident, the length along the axial ray, right? Then you have the correction. So we're talking about maybe some phase along this surface. So what's the phase here? Maybe, okay, let me draw that. That might be a good thing to draw. So we have this, that, and that. So here at some R, what is the phase there? Well, it's the phase of the axial ray, right, to this point, plus the surface quadratic approximation of that surface, right? So we have to propagate the Q matrix to that point, Zi, right? This Zi is defined with respect to this local origin that has 0 Z there, right? So we have to propagate the Z matrix up here, or the Q matrix up here, and then we get that if we use this Q matrix, which is propagated to that point, to this point, right? This is Zi, this distance. Then we can form a second order approximation at this point in the pencil, right? All right. And by moving along these tangents, so the wavefront surfaces are parallel surfaces. So the principal directions of this surface down here and this one, say W, or this one's W naught, let's call this one W, yeah? Are the same, right? So that means that the Q matrix remains diagonal, and moving along this coordinate system x1 from here now to like some point, I guess it's to the point there, right? So this drawing's kind of getting, so it's this point here. This is x1, this is x2. We move to this point in this coordinate system, right? That's x1 incident, x2 incident. Really, it's the x1 incident, x2 incident components of that vector, right? But projected into this plane because these are the same, these are parallel to this. All right, and then the curvature matrix allows you to calculate the phase there, right? Yeah? Okay, good. So, good. So now we have to introduce this other paraxial ray because why? Why do we have to introduce that all of a sudden? Because we're not talking about a scalar function. Now we're talking about vector functions. We want to talk about these vector amplitudes, and the vector amplitudes have to be orthogonal to the ray. We know that, right? The zeroth order solution is always orthogonal to the ray, the electric field. Because del, or the gradient of S dotted with E naught is equal to 0. We derived that. So now we need to form a new coordinate system over here that has orthogonal vectors to the ray and longitudinal vectors to the ray, so that we can describe the electric field with orthogonal components there. And we find these three vectors in terms of the base vectors and the coordinate system at this origin, and the components there, right? And the radii of curvature and so forth. Okay? Very nice. Now we can describe the electric field in this coordinate system, sigma 1, sigma 2 gradient of S. All right, now we introduce a third coordinate system, so there's a reflective pencil as well. The third coordinate system is located on the surface, because we need to, okay, so you'll see why in a second. We need all three of these coordinate systems.
Reflection. We need to see the curvature for
Yeah,
like a normal.
okay, to jump ahead, we're gonna apply a boundary condition. N crossed with E total equal to 0 on the PEC screen, right? But that's for R on sigma, for points on the PEC surface. So we need to be able to describe the incident pencil's wavefront along at different points on the surface, right? And the reflected pencil's coordinates on the different points on the surface, right? Because we have, I guess that should be reflected, it's probably better. All right, so we'll get there. So we have to describe a third coordinate system here where all the stuff on the surface for reflection is going to take place in this coordinate system, the one centered on the surface at point O. What we're going to have to do is describe the incident pencil in terms of these coordinates. That's what we're going to do. That's going to be the only hard part, right? So let's do that. All right, so we define this third coordinate system, x1 sigma, x2 sigma align with the principal directions so that the curvature matrix of the surface is diagonal, and we have a z direction, right? We have an incident pencil here with its z-axis like that, the axial ray, and then we have a reflected pencil here with its axis along the reflected axial ray. Then there's also the sigma local coordinate system, which we'll probably need. All right. Okay, good. We can determine the reflected field now. So to determine the reflected field on a reflected ray, it is necessary to know the curvature matrix of the reflected wavefront, right? At some reference point on the ray, and the initial values of the electric field, because we now know how to propagate an electric field along a ray. Propagate its phase and its amplitude. We need the curvature matrix, gives us everything, right? So we're after the curvature matrix of the reflected field, right? All right, so how do we determine the reflected curvature matrix? We use the concept of phase matching. So to determine the reflected curvature matrix, we have to apply the boundary conditions on the PEC screen. Namely, n is this n, right? So n here, n to the surface, or this one in particular, n. N, so it could be at different points, right? We're talking about this point neighboring to O. So everything doesn't happen at O, right? If it was just axial rays, then we'd only have to consider O. But we have to consider neighboring points around here. So there could be another point R on sigma that we have to also satisfy the boundary condition and phase matching. So we need a local coordinate system there. And that one has n, right? So n crossed with E incident plus E reflected or E scattered has to equal to 0 for R on sigma. All right. So that boundary condition can only be satisfied if the phases of the incident and reflected fields are matched over sigma. That's called phase matching, right? You undoubtedly have heard of that. All right. So all we have to do is compute this now. So let's do that. All right. The coordinates of R can be described by a position vector drawn from O to some point. Let's say this is R here, right? In the coordinate system of the surface. All right. And Z sigma here is given by the second order quadratic approximation of the surface at that point, right? Okay. To calculate S incident at R, so now we're talking about any point R on this surface, which has this form and this Z. At any point, we need to evaluate S incident there, the incident pencil at this point, right? Okay. It is necessary to know the corresponding coordinates, x1 incident, x2 incident, z incident of R, expressed in terms of these coordinate vectors, because everything's going to be done in this local coordinate system on the surface. All right, so how do we do that? We have an incident pencil, right? There's an incident pencil, there's some paraxial rays here, right? We want to be able to find what are the incident pencil coordinates in terms of these vectors here, the surface vectors, x sigma 1 sigma, x2 sigma, x3 sigma. Basically, we have an incident pencil, right? Which is a flux tube of rays and has its own coordinate system, axial ray and the x1 incident, x2 incidents, right? Now, we can define the phase of this pencil anywhere in the pencil using this coordinate system. But we really need to know what the phase is on that surface. So we need to express these coordinates in terms of these vectors so that we can then find the phase of the incident pencil on the surface sigma. Yeah? Okay, so that's easy to do, right? All we have to do is take the dot product of R expressing this sigma. This puts you on a surface somewhere, right? This is on the surface, R, with the incident field vectors, right? All right, good. So that's going to introduce x1 sigma, x2 sigma, and z sigma, and it's going to express the coordinates of the incident pencil in terms of these base vectors. And the z incident is R dot of z incident, yeah? Does that make sense? Yeah? Everybody? In the back?
You're doing this just for the axial, right?
No, you do this for, this is the coordinate system actually, as a matter of fact. So this is just the vectors. Okay, so this point R here, right? This point R has this form here. So it's in terms of these vectors and these components. What is that point in terms of the incident field, incident pencil coordinates? Right? So here's some incident pencil, right? Let's say it's wide enough so that this point's encapsulated. What is this point of the incident pencil coordinates in terms of the incident pencil coordinates, right? Does that make sense? This point is expressed in terms of these vector components, but what is this point expressed in terms of the incident pencil coordinates? So that we can evaluate the phase of the incident pencil coordinates at this point. Clear?
So if we have a point in a surface.
You have a
we can
point-
find what is the point with respect to the actual.
We want the phase of the incident field at that point, right? So we know how to describe the phase in terms of the basis vectors for the incident pencil.
Yeah.
But we want to know what are those components of the incident pencil? How far do we go along x1 incident, x2 incident, and z incident in order to get to this point, which is described in this coordinate system by this vector, right?
Yeah.
So those components are here and here. Okay.
Basically, you're transforming like two local coordinate system.
Yeah, it is a transformation. That's exactly right. Right? We're transforming some vector in the
Of the surface.
surface coordinates into components in terms of that same vector. So this same vector, right? This vector in terms of the incident pencil coordinates x2 incident, x1 incident. What is this vector in terms of this coordinate system? Yeah? Okay. So we got these expressions, right? Let's introduce this notation. We're doing a bunch of dot products. So x1 sigma dot with xn incident, x2 sigma dot with x, n incident. We're going to define this notation p, a scalar, mni, as xm incident dot with xn sigma. So we can write this compactly as this, right? And then the z part is here. So the first expression, this one, is nothing but this, x1 incident, x2 incident, so n equals to 1 and 2, so if this is 1, right? Because this is for two n's. That's equal to this projection matrix multiplied by x1 sigma, x2 sigma. And then we move the z dot product over to this one, all right? Or actually the z dot product, yes, okay. All right, and then the z dot product has z incident dot with x1 sigma, so z incident dot with x1 sigma, z incident dot with x2 sigma, and we have 1/2 p33 x1 sigma x1 sigma, and we have, okay, so this is the local surface approximation of this, right? Of the surface in terms of the sigma coordinates. So that gives you the difference from the surface with respect to the tangent plane, that epsilon thing, right? Okay, there's a lot here. You probably won't, fully grasp it as I'm telling you it, right? You need to go back and think about it and read these things and study them, okay?
Does that mean like the PI33 would be ZI dotted with Z epsilon?
Yes. So that's right. Z dotted with Z is P33, right? So this is P33 incident is XM3 dotted with X, or X3 incident dotted with X3 sigma. Which are the Z's, right? Good. All right. So let's substitute this into the incident pencil. And we obtain the phase function of the incident pencil, but now in the coordinates of R on sigma, right? So that's the whole point. Here's S incident, the incident pencil coordinates. We know it's with respect to the phase reference, plus now we have this expression, Z1. So this is normally the Z, right? So remember, if we go back and compare to our incident pencil, where is that? Here. The second term is Z, right? And the third term has x1 incident, x2 incident. But now we want to express it as x1 sigma, x2 sigma. And this Z is going to express in sigmas now too, right? So we have x1 sigma now and x2 sigma and Z dot with x1 sigma and Z incident dot with x2 sigma, right? So this is the new Z, but now expressed in terms of the screen coordinates with R on sigma, which is what we want. We want the incident field at whatever point we point to on the surface from the surface coordinate system. And then here we have x1 sigma, x2 sigma now. But we have these matrices, the projection matrices, because we need to express a vector in one coordinate system in terms of the components of another. Here's still Q incident because the incident pencil. But now we introduce Q sigma. The surface curvature matters. Right? Because the incident field has a wavefront that's coming like this, and then the surface does too. The surface has a shape. So the phase is not only the tangent plane of the incident wavefront has an epsilon, second order quadratic approximation. The surface does as well, so you have to add both of those. Right? Okay. We're almost there, guys. Now we just got to do the same thing for the reflected in exactly the same manner, the reflected pencil. All right? Where we're defining the x1r and x2r align with principal directions of the reflected pencil. Okay, but we don't know what the principal directions of the reflected pencil is yet because we have no Q matrix for that yet, right? We're gonna circumvent that problem, so don't worry. We'll come back to that, all right? All right, now we can do phase matching because what was our boundary condition? S incident equal to S reflected at all points R on sigma. R on sigma, right? The R's here, this R and this R have to be on sigma. But now we have both the reflected and the incident pencil in terms of these sigma, these coordinates, in terms of the coordinates of R, the point R on sigma. All right. Oops, here. Yes. Okay. All right. So we have the incident, we have the reflected pencil as well, right? Okay, now we can do the phase matching. So let's match it up. So S incident is here, and that equals to S reflected, all right? And now everything's in the same coordinate system, so we can do the matching. They're all in the surface coordinate system, sigma, right? All right, so let's match up linear terms first. What do we get? What are the linear terms? Which one?
Second thing.
These are the linear terms, very good. You match these ones up, what do you get? You get Snell's law of reflection. Means that the tangential components have to be equal, right? Or sorry, the angles of z dotted with x and sigma of the incident pencil has to equal to z dotted with x and sigma of the reflected pencil.
With respect to the normal of the surface.
No, not this stuff.
Yes, right. So this is Snell's law of reflection. Theta incident equals theta reflected, right? This is theta, right? That is z dotted with x and sigma. Yeah, that gives you, it depends on, it's related to theta, right? It's one of the angles of incident. It might be respect to the, not with respect to the z-axis of the normal. Yeah, that's right. Okay.
Well, how did you find the reflected principle?
All right, we'll get to that. Very good. So the linear terms give us Snell's law of reflection, and the consequences of Snell's law of reflection are we can define the reflected z. We know the reflected z now because of Snell's law for the axial ray, right? So the z, that gives you, this is the Snell law thing here. And we can say that P33 incident is equal to negative P33 reflected, which is the angle of incident equal to the angle of reflection, right? That's basically what this says, right? That's P33. All right. Now, matching the quadratic terms. So this is the quadratic term of the incident, quadratic term of the reflected. All right. Okay, since we do not know the principal direction, of the reflected pencil a priori, we can define two arbitrary directions to start. And the ones we're going to choose are reflecting the incident x1 and x2 from the surface sigma at O. So just reflect them, right? Okay, that means xn reflected is defined like this. We'll start like that, right? What's going to happen? We're going to end up with a reflected Q matrix, which is full, right? We're not in the principal coordinate system. So we'll have to rotate after we reflect to find the principal direction. We can, from the reflected Q matrix, even if it's full, you can find the principal directions. All the information's in the Q matrix. So this choice results in a left-handed reflected pencil coordinate system that's perfectly acceptable, but it leads to P incident equal to P reflected as well. right? The incidence xy are equal to x1, x2. Incidence equal to x1 and x2 reflected. They're equal, so their projection matrices are the same. So now we can solve for the reflected curvature matrix because P incident is equal to P reflected, and we saw here that P33 is equal to negative, P33 incident is equal to negative P33 reflected. All right, so we do that. So here's the matching of the quadratic terms. Now we're going to change P reflected to P incident, P reflected to P incident, and P33 to minus P33 incident, right? Cool. All right, now you can solve for the Q matrix at Z reflected equal to 0, which is what we need, right? Because we can propagate it after that easily. Is equal to the Q matrix of the incident field at Z equal to 0, plus this projection, which is dependent on the surface curvature of the reflecting surface, the screen, right? Good, that's it, man. So now we have the Q matrix of the reflected field. Since we picked arbitrary reflected pencil coordinates, directions rather, not coordinates, directions. We picked these ones, right? Arbitrary directions for the reflected pencil. The above matrix may not be diagonal. So we know how to compute the principal directions given a Q matrix, noting that we can define RU and RV of this reflected surface, the wavefront, as these arbitrarily picked, right? Or they were picked in this way. Then we can find, once we have this and this, we can find E, F, G, and then we have the Q curvature matrix. We can find the trace. We can find kappa G and kappa M and kappa G and kappa M, determinant and trace of that Q matrix. This Q matrix here. Then we know the entries of the Q matrix. We can find kappa 1, 2 from kappa M and kappa G, which come from the Q matrix. And therefore, we can find alpha and beta. And we have gamma 1, gamma 2. And we can find then the principal directions after we reflect. All right? Okay, so it's not that crazy. It's a lot of derivations, but we had to do the derivations, right? So really what you do is you launch a ray from some source, and it's a straight line. So you think you have to integrate sigma, but you know the length of your ray, right? So you have to solve at the point of intersection from your ray and the surface. You do that in software, right? Solve a system of equations. You find that point, then you know the length of the ray. You know the initial curvature matrix based on your source. So then you know the curvature matrix and the phase at the point of reflection, right? Now now you can calculate the reflected Q matrix like this. You have to find the EFGs of the surface, create its curvature matrix. Then you need the EFGs of the incident field, and you can find its curvature matrix. Then you need these projection matrices, and those are easy to do because they're based on the principal directions. So you find the principal directions. You have some surface, sigma. You find the principal directions at some point, right? Find these principal directions. Okay. X sigma 1, X sigma 2. So you find EFG and all that. Find its Q matrix. Then you have these principal directions. So now you know, and then you know the incident field, right? We said we had an incident field which has a Q matrix that we know. We know the length of this ray. And we are going to define the principal directions of the incident wavefront because we know the Q matrix of it, right? So now we can find these projection matrices because we know this, and X1 incident, X2 incident hat, right? We know all of that. We can find all these matrices. We can find this. We know this. We find the reflected Q matrix, right? Once you find the reflected Q matrix, then we just have to go to, where is that? Here. Nope. Here. Nope. Here, sorry, here it is. Once we have the reflected Q matrix, we can propagate the electric field. We find the radii of curvature from the Q matrix. We can calculate the divergence factor. Then we know the length of the ray, the next intersection point is going to be, and then we can propagate the ray. Right? It's not that much. You'll do a problem like that. All right. Okay. I'm sure you're getting overwhelmed, right? There's so much here. What are we on? Slide 80 something, right? We haven't solved any problems yet. 89 slides in differential geometry. Don't worry. All right, do the homework problems and try to pick up the concepts, and we'll do some examples where we solve problems in geometrical optics. All right? That'll be your next homework. Combined with diffraction. That'll be the last homework. All right? Okay, but study these things, right? Don't wait for those problems. Take a look at these. Any questions? All right. See you guys.